Hello everyone, I'm Jundan. Very happy today to share our work Intrinsic Diffusion, a joint diffusion model for intrinsic image decomposition. Part of this project was done during my internship at Adobe. Let's begin with a brief introduction to intrinsic image decomposition. This is a technique to estimate physical properties from a single input image. The decomposition can be formed in different ways. In our work, we choose a popular one and assume the scene is pure Lambertian. For a Lambertian scene, the input image is decomposed into an albedo image multiplied by a shading image. Our work also estimates surface normals. Now, having these physical properties, we can do several photorealistic image editing applications. For example, we can manipulate shading layers for relighting. We can also manipulate albedo layers for retexturing. Intrinsic-based image editing is explainable. It allows users to change certain physical aspects while keeping others untouched. However, this problem is still challenging, as the decomposition is highly yield-posed. Current deep learning solutions still rely on some empirical assumptions to make things easier, but these assumptions are not always useful. For example, grayscale shading and smooth shading are two popular assumptions for shading estimation. As the previous pinate assumes lighting is grayscale, it cannot capture the color of the light source, but our model can do it. Also, as nearnet assumes shading is mostly smooth, some shape variations are ignored, like the blanket on the bed. Its folds are ignored by this previous model, but our model can estimate complex shading for this soft fabric. And another common assumption, albedo should be piecewise constant. This assumption has difficulty reconstructing detailed textures, like the wooden floor pattern in the example. Our model can estimate fine-grained albedo. In addition, many other priors are still used in recent learning-based frameworks. While they perform well in specific cases, they may fail in others. This raises the question, can we move beyond the assumptions and develop a more general solution? The answer depends on how many training data we have. We need a diverse and large-scale dataset to handle this yield-posed problem. Although training data for intrinsic image is limited, we observe that billions of training data is available for general image generation. Besides, a pre-trained text-to-image generation model has already learned some implicit intrinsic properties. As shown, when given text prompts describing different lighting conditions, this pre-trained latent diffusion model changes the surface appearance accordingly. Now we have the question, can we make use of its learned knowledge, and how can we repurpose this pre-trained diffusion model for our task? In our project, we propose to treat intrinsic image decomposition as a conditional generation problem. This is an overview of our proposed approach. It is based on ControlNet, but uses a new conditional scheme. To be specific, our pipeline has a pre-trained and fixed latent diffusion and a trainable ControlNet. ControlNet is a technique to introduce additional signals to control the image generation process. And for our approach, we use two types of control signals. The first is text prompts, that is albedo, shading, or surface normal. Another is domain-specific condition embeddings. This condition embedding is extracted by an image encoder, which I will introduce later. During inference, the model generates different intrinsic image layers based on different control signals. As shown, when we provide the model with a shading text prompt and a conditional embedding for shading, it generates a shading image accordingly. If given other text prompts and a conditional embedding, the model can generate images in the other two domains. Using this control scheme, we only need to train one joint model to predict consistent images in three different domains. The conditional embedding is very important, as it's the only data path containing a description of the input image. We need to generate a shading layer that closely matches the original input. In our experiments, we found that the original ControlNet's condition embedding couldn't capture the required dense features. To address this, we propose a new conditional image encoder. This new encoder has shared residual blocks and 3 separate transformer branches. Each branch specializes in extracting features for a specific image domain. Our new conditional image encoder is more powerful than the original one. Here is an outline study. As shown in the second column, using the original encoder, the model cannot generate correct albedo colors. Most color information is lost. The albedo appears almost grayscale. By contrast, our proposed encoder helps generate a colorful and high-quality albedo. We would like to highlight the benefits of our proposed joint learning framework. First, we can combine various data sources with different types of annotations. This means we don't need fully annotated training data. Either one of the ground truth intrinsic layers can be used for training. And second, training with surface normal data improves the overall performance. As shown, the duet should have constant albedo in the red circled region because the materials are the same. And the shading should have strong variations due to the folds. However, without surface normal, the model cannot separate intrinsic layers properly. It is important to note that this is a challenging case to the traditional shading smoothness assumption. A model must learn to identify geometry variations to manage such cases. Our final model naturally achieves flattened albedo and strong shading variations. Finally, our model achieves the best performance in 5 out of 7 dense metrics on the synthetic dataset. We have also compared ours with the previous methods on the real-world dataset using perceptual metrics. Please refer to our paper for other experimental results and explanations. Here, I would like to share some qualitative results. For the surface normal estimation, our model can predict high-quality, consistent normal with details. Even though we trained our pipeline at a resolution of 384, the model is stable when working with higher resolutions. It performs well under common illumination and also in dark environments. This is a comparison between our model and other concurrent diffusion models on albedo estimation. Please focus on the pillow with the letters C and H. You can see that other diffusion models struggle to reproduce these letters in their albedo. The results are blurry, and the letters are unrecognizable. In contrast, our model generates a clear C and H. That means our predicted texture better match that in the input. This is attributed to the more powerful conditional image encoder we proposed. In the end, I would like to show an application of HDR brightness adjustment. Given an LDR input image, we first estimate its albedo and shading. Then we adjust the shading. We adjust the input brightness by reducing the brightness of shading. Please focus on the saturated regions on the wall. Now I reduce the brightness by 50%. In the reference image, the wall becomes clear. Again, reduce the brightness by 50%. We see that our model achieves similar brightness adjustment results compared to the reference. The saturated region decreases and the wall becomes increasingly clear. This application requires the intrinsic model to recover the lost albedo information. Diffusion models are very good at implanting the lost information. Moreover, shading should be reconstructed with a high dynamic range. Our model performs well in both albedo estimation and shading estimation, so it can enable this application. We have other demos on our project webpage. Here is a web link and my email address. As we wrap up, I would like to thank you all for your interest in our work. Please feel free to visit our website or contact me for further information or discussions. Once again, thank you all for your time and attention.